Okay, so thank you for joining me this week. I've started the recording, so as always, at this point, you can type your name into the chat, and we'll have a record for your attendance so that we can get you your data correctly for the next session. Well, it's good to see everybody, and thank you to everyone for being on time. It's nice to start on time so that we can finish on time, and so that we don't have to rush through things at the end. I hope everybody had a nice week and a good weekend.
Afternoon.
And I'm
Afternoon.
looking forward to finishing up our little
Good.
mini workshop on circle theorems, and then finish up our mini workshop on circle theorems, and then we'll begin kind of the preliminary planning for the integration and differentiation workshop, which will go for one or two more sessions after this before we pivot to WAS and WIT's math competition material. Okay, so yeah, so thank you again for all coming. I got not very many solutions to the exercises that I gave. I got one, but from somebody who's not here right now. So all right, so we'll go through them. But before we go through them, I want to recall a little bit of what we did last week. It seems like the network problems last week were more severe. They're maybe not so bad today. So let me just do kind of a quick recall of what we were mostly doing last time. We were talking about circle theorems, and most of the day, at least most of what we're going to talk today, was going to be theorems about angles. And so we have all sorts of different ways of forming angles inside circles. And I just want to review and recall, what are all the ways we have of doing this. So the first case is what's called a central angle, right? So how do you do a central angle? Well, that's if I draw a circle and then the center of the circle is O, and I have an arc A that goes from point A to point B, and I draw the angle that connects the center O to point A and to point B, then this here is called a central angle. Okay? And we saw last time that the measure of the arc is the same thing as the measure of the angle. Okay? So and this is just a definition. This is just how we measure an arc. So if this angle is looks like about 60 degrees. So if this angle is 60 degrees, then we say that this arc is also 60 degrees. Okay? So this was called a central angle. I'll write this in red. So central angle. Okay? And then we also had what we called an inscribed angle. So I'll draw the picture over here. Okay, so if I have a circle here, and now if I have point A, point B, and point C, and I draw the angle that I get from connecting A and B, and then from connecting B and C, this is called an inscribed angle. Okay, so this is called an inscribed angle. I'll write this angle over here. And we proved last time, and it was actually a fairly complicated proof. I mean, not that complicated, but it took a couple of steps that the angle over here has half the measure of the arc. So if this arc measures, I don't know, if this arc measures, let's say 90 degrees here, then the angle is going to be 45 degrees. It's going to be half the measure of the arc. Okay? So these were the two, main kinds of angles that we talked about. And we said again, the first one doesn't need to be proved because it's just a definition. To say what the measure of an arc is, it just means the definition of the central angle. So if this angle is 60 degrees, this arc by definition is 60 degrees. Whereas for the inscribed angle, then that's actually a theorem. Okay, once we know what we're basically trying to show is that the central angle corresponding to A and C is going to be double the measure of the inscribed angle corresponding to A and C over here. Okay, so this is just a recall from last time. Any questions?
Yeah.
Yeah,
Yes, sir. Yes,
great.
sir.
Prince, yes.
Yeah, I'm wondering as well, B to C can be an arc.
B to C is also an arc. Yes. So
Okay,
this is an
okay,
arc, but there's no angle drawn in the picture whose measure is that arc, right? So
okay,
if you wanted the arc from B to C is definitely an arc, but if you wanted an angle that was related to that arc, you'd have to draw angle BAC. You'd have to complete the triangle. So if I completed the triangle over here,
okay.
then I could
O-
look at arc BC, and this angle BAC here would be half the measure of the arc BC.
Okay, so in the same vein, if you draw a line from C coming down to B, and then you draw, make it like a triangle
Hmm.
to form an angle there, can it be?
Yeah, I mean, so these are all the lines, right? So this angle is going to be half of arc AC. This angle is half of arc BC, and this angle here is half of arc AB, right? So each angle is half of the arc opposite the angle. So the one that is where the two lines that make the angle, where those lines meet the circle, that is the arc that you have to take half of to get the angle measure. So we'll see this
Okay.
in the example. Other questions? Okay. So there was a couple of more things to review before we go over the exercise. So the first one was if two, I'm going to just label these one and two so that we have a diagram that corresponds to both of them. So the first one says that if two chords A, B, and C, D meet in a circle as shown below, so let me draw the circle. So this is going to be picture one. So if two chords A, B, and C, D, so I'm going to say this is A, B, and this is C, D, meet in a circle drawn below, then if I take this angle over here, this is the angle that I'm going to mark, then the measure of the marked angle is half, or it's the average of arc AC and arc BD. Okay, so we did this last time. So you have to take this, the arc subtended by the angle, and also the arc opposite that. And it's going to be the difference between those two arcs. And then the second diagram is if you have a chord that meets a circle at its tangent line. So let me make a circle and let me draw a tangent line. So purple. Okay, so if I have a chord that meets a circle at the tangent line, so let's say this is B and this is A, then if I draw the line AB, so I have a chord AB of a circle and it meets the tangent line to the circle at B, then the measure of the angle formed, this is the angle over here. Maybe I should label the angle in green just to distinguish it from the rest of the picture. I'll label the angles in green. So then the measure of this angle is exactly half the measure of this arc. Okay, so these are the sort of more advanced angles. You have your basic ones, which are your inscribed angles and your central angles. And now here, there's other ways of making angles. You can make an angle formed by two chords. And this is not a central angle, right? Because this point is not necessarily the center of the circle, right? This could just be any point where these two chords meet. But the result is valid regardless. And then over here, this is just some chord and some tangent line. Again, it's not really an inscribed angle, and it's not really a central angle. It's a different kind of thing. And yet still we have a similar looking theorem that the measure of this angle is one half. Hey, what's up? Leaning on my bar. Oh, sorry. Oh, sorry. Oh, sorry. Sorry. Okay. Okay. Scared me. Okay. All right. All right. So that's how this works. Okay, so any questions on these two? This is also just recalling from last time.
Yes, that
Yes,
Bruce.
Princeton?
Yeah, the tangent, the circle with the tangent line. I'm not understanding. Actually,
Hmm.
are you
So,
saying the
okay.
net? half of the B is equal to A. That what you saying? If the measure is given.
Yeah, so this angle, so let me draw another point here. I'll call it C. So the theorem here is that the measure of angle ABC is equal to 1/2 times the measure of arc AB. So for instance, if this arc is 120 degrees, then this angle will be 60 degrees. Yeah, so that's what it says. So the measure of the angle is half the measure of the arc. Okay, similar to an inscribed angle, right? It was the same thing with an inscribed angle. The measure of the angle was 1/2 the measure of the arc. Okay, so for this tangent line, it's the same looking kind of results, right? The measure of the angle is 1/2 the measure of the arc. Now, the measure of the arc, whatever it is, it would be if you drew a central angle, that would be the measure of the arc, right? But in general, we can think of measures of arcs as just what fraction of the circle they are, right? So if the whole circle is 360 degrees, then if this arc is, 1/3 of the circle, then that's 120 degrees. If it's a quarter of the circle, it's 90 degrees, and so on, right? You can just think of the arcs as just being a part of the circle where the whole circle is 360 degrees. Okay.
Okay.
All right. Is that
Thank you.
okay?
Yeah,
Good.
a
Yeah,
question
Prince?
that yeah. If we take a line from point A
Hmm.
and bring it down and make it to be C.
So if I
So
drew
we
a line from A to C,
you have to bring it down from point A to create another arc
yeah. So if I drew this like that,
from point A to no.
no,
To bring it down to what you see 1/2 the measure of AB.
right,
You
measure
have
of AB.
understand?
Yep.
You have to bring it down here.
Okay, so the M here just means measure. That's not a it's not a variable. It doesn't M just means measure. Okay.
Okay, no problem.
It's
I'll get
okay. It's okay. Yeah, M just means measure. So this is just a way of saying measure of arc AB. If you want to, notations vary. You could just call this 1/2 AB if you wanted to. The reason people say measure is that sometimes if you don't put the M, then people think you actually mean the arc length, like the amount of distance here in the arc. And that's not what you want because you want a number of degrees or radians. You don't want an actual distance. So that's why the M just means measure. Okay.
yes, Dada Obus,
Okay.
Princeton.
Yes, Princeton.
So it's possible that two tangent lines run on the same circle at the same time?
Yes, we will. I'll show you that. You mean like if I had a tangent line from C to B and then another tangent line from C to some other point?
Yeah.
Yeah. So that can happen. That's not this theorem. We'll talk about it in a little bit.
Okay. Thank
Yeah.
you.
Good. Other questions? Okay. So at this point now we can go and do the exercises, which I think Princeton submitted the solutions to. So let me draw the figure here. So in this figure here we have a circle and I have a tangent line like this. Good. So this is going to be A and this is going to be B where the tangent line hits the circle. This is going to be C. Okay, and then I have D. And then I drew the line from C to D. So I'm drawing a triangle here. And then we're given in this triangle that angle ABC equals 60 degrees. So I'll fill that in. This is going to be 60 degrees. And angle BCD here is going to be 70 degrees. Okay, and the question is find the measure of angle CBD. Okay, so there's a few ways that you can do this. But the point is, we're going to use these theorems that we've recalled at the beginning of the lecture in order to do this. Oh, another line segment. Oh, sorry, from the previous thing. Draw a line segment from point A downward. I mean, okay, yes, you could do that, but It wouldn't really have anything to do with the diagram or with the theorem. Um, yeah, to go back here, sorry. Yeah, I mean, sure. I mean, we can draw a line downward, but there's it wouldn't really do anything. So, okay. So let's go back to this example. Okay, so we've got 60 degrees here and 70 degrees here, and we want to find this angle. Okay, this is our extra angle that we want to find. Oh wait, sorry, not that angle. CBD. We want to find this angle. Okay. So how are we going to do that? Um, any um, any guesses?
Yeah, let me try that.
Sure. Mm-hmm.
Yeah,
Yeah.
so we find a sum of the two angles and
Mm-hmm.
we divide by two.
The sum of the two angles and divide by two, but of which two? You mean the 60 and the 70?
Yes, 50 and 70 divided by two.
Okay. So what result are we using to allow that, right?
So we will say angle CBD is equal to angle ABC plus angle BCD. Half angle ABC
Mhm.
plus angle BCD.
Okay. I mean, I think that that's not really a result that we have, right? I don't see any reason why we're allowed to say that.
Yes,
Right. So I think if we're going to want to do it, we're going to need to use something. I mean, there's a few different ways to do this, but we're going to need
yes,
to use
that's
something
obvious.
about the arcs, right? Yeah.
That's obvious.
Yes, Princeton.
Yeah, I think we are using a circle that include a triangle within a circle. So I've been inscribed in the circle now. So a triangle that is inscribed in a circle is equal to 180 degree. So
Sure.
that's the first thing.
Yeah.
Secondly, measure angle ABC
Yeah.
plus measure angle DBC.
Yeah.
Yeah, plus then we are asked to find measure angle BM
Yeah. So
plus
should I
measure
label
angle
an
B.
extra point here? I'll label a point E down here.
Yeah, yeah, okay, no problem. So it would be measure angle CBE,
CBE or DBE?
DBE, sorry,
DBE. Yeah.
DBE, yeah, equal to
Yeah.
180 degree.
Great. So this is a great thing to begin with, right? If I take all three of these angles together, right? One, two, and three. So this is ABC, DBC, and DBE. Then the entire thing is 180 degrees because it's a straight line. So that's going to all be 180 degrees. Excellent. Good.
So,
So,
so
okay.
now,
So now what else do we know?
so now measure angle ABC now will be 60 plus 70
Well, okay. So
plus
60, I agree with 60. Okay. So measure angle ABC is 60. Oh, wait. So sorry.
60
So that's 60 degrees plus now angle
plus,
DBC. That's what we want to know, right? So we'll leave that by
yeah.
itself. And now angle DBE. How do we know? Well, I'll just write plus angle DBE for now equals 180. Okay, so now what else do we know, right? Because angle ABC is 60 degrees. That's given to us. Okay, so right. So this is the right. Once we figure out what oh, maybe I'll call this CBD just to keep the notation correct. I'll just call it CBD. It's the same thing as DBC. So if we can figure this, then we win, right? So the question is, how can we figure out angle DBE?
Yes, so that was.
Yeah, Princeton, Linford.
Yeah, so our target is to find angle CBD, right?
Yeah.
Yeah, so per my calculation, I derive at 50. And
Hmm.
then, yeah, in getting that, we are giving that angle BCD is 70
Hmm.
and angle BDC is 60. Yeah, so
ABC is 60. Yeah.
so we use the triangle sum rules, which is A plus B plus C equal 180
Hmm.
over the cycle. Yeah. So we say angle B, DC is equal to 180 minus
Okay. Okay,
70
so
Okay.
yeah.
and 60. Okay, so the 70 and 60 in parentheses, because the 70 and 60, they are both angle BCD plus angle BDC. So the sum
Okay,
of
okay. So
angle
let's see this for
BCD
a second.
is
Okay, so
equal to
sorry.
180.
Okay, let me try to write down with you at the same time. So you're saying first we have that angle CBD plus angle BDC plus angle
Good.
DCB is equal to 180 because this is all the triangle, right? This is what you're saying, right? And we know that this is 70 degrees. This is what we want, right? I mean these two angles are equal here. And now, so the question is, yeah, that this angle CB, oh, sorry, no, that's what we, that's not what we want. Sorry. This is what we want over here, angle CBD. And then, so this angle BDC. So how do you know anything about angle BDC? Right? I mean, again, if I could know what angle DBE is, then I'm good. And if I know what angle BDC is, then I'm good. Um, oh, so I see. So from this, we can get, if you want to, that well, okay. I'm still not quite sure where you go from here. Where are you getting your 50 degrees from?
The angle BDC, right?
BDC. Yep.
Yeah, it's 60 now. Let's
Why
look
is it
at
why
what
is
was
it
true.
60? I mean, I agree with you. It is 60, but why? Why is BDC 60?
Yeah, okay. It's located on the arc, on the core, rather, on the core. So
Yes.
angle for A, B,
Hmm.
and C. Yeah,
Yeah.
angle BDC. I wish my camera was there so that I can just flap
Yeah.
it on the sheet.
Yeah.
Yeah.
So this is good. Yeah.
BD,
Yeah.
yeah, which is 60.
Yeah.
60 in the sense that they
Hmm.
are interior angle, if they are
Hmm.
equal. Yeah, yeah.
Okay, perfect. So you know what I'm going to do? I'm going to even get rid of this. We're going to start with your line because I think it'll be a little faster, a little easier, right? So CBD plus BDC plus DCB is 180 degrees. This is because they're angles in a triangle. Oh, what just happened? What just happened? Sorry about my screen share just ended. Sorry, give me a second. What just happened here? What? Okay. Um, okay. All right. Okay. Good. Okay. So because these are the angles in a triangle, they add up to 180 degrees. DCB is 70 degrees. That's given to us. So now, as Linford said, let's look at the arc BC. Look at the measure of the arc BC, right? So what do we know about the arc BC? We know there's a 60 degree here, which is formed by a chord and a tangent. So that measure of the arc has to be from the theorem, it has to be twice as much as the measure of the angle, right? Because this is our theorem that we have from before. If you have an angle like this, the arc is twice as big as the angle, or in other words, the angle is half as big as the arc. So this is going to tell us that the measure of angle BC is equal to 2 times 60 degrees, or 120 degrees. But now, as Linford said, right, we have this angle BDC, which is an inscribed angle that has the same arc, right? So BDC, it's the same arc BC as this angle ABC. So that means that both of them need to be the same. So we also have that angle BDC equals 1/2 the measure of arc BC, which is equal to 1/2 times 120 degrees, which is 60 degrees, because it's an inscribed angle. Okay, so this is the key observation, is that you've got one angle formed by a chord and a tangent, and another angle that's an inscribed angle, but both of them have half the measure of this arc. So they have to be equal to each other. So I'm going to add it in over here that this, we figure out that this here is actually 60 degrees also. So this is the
Yeah,
key
done.
observation. This angle and this angle have to be the same because they come from the same arc. And now that we have this, now the rest is just algebra, right? So now we have, so angle CBD plus, well, BDC is 60 degrees and DCB is 70 degrees equals 180 degrees. And when you solve this, you end up getting that the measure of angle CBD is 50 degrees. Okay, so the key is this one's given to you. This one you can figure out from this reasoning that if this is 60, then this also is 60. And then your last angle there is what you want to figure out. Once you have angle CBD plus 60 degrees plus 70 degrees equals 180 degrees, then you're in good shape. Then you just subtract the 60 and the 70 from the 180 and you get 50 degrees on the other side. So this turns out to be 50 degrees. Okay, good.
Yeah,
Any questions?
yeah, question, sir.
No. Okay.
Uh,
All right. Clear for everyone?
yeah, in case the tangent now is removed,
Yep.
and then we have this the instruct angle. So
Mhm.
we'll be looking at the same process I will follow.
Yeah. Right. I mean, if the tangent line was removed, the problem is if all that I gave you was that this one angle here was 70 degrees, then you wouldn't have enough information to solve the problem, right? And if I gave you that this was 70 and this was 60, then the problem would be very easy because it wouldn't have anything to do with circles at all. It would just be here's a triangle, one angle 70, the other 60. What's the third angle, right? You don't need circles to do that. The reason the problem is given this way is because you need to use circles to show that you actually know the second angle of this triangle. To do that, you need to have a circle theorem. Okay, that's why you can get this purple angle here. And then once you have the two angles, you can get the third angle in the triangle. Okay. Other questions? Okay, let's move on. Okay, homework exercise 2. Suppose that we have a quadrilateral ABCD inscribed in a circle. So I'm going to do A, B, C, and D here. Okay, so this is just an arbitrary quadrilateral. I'm not claiming that it's a square or a trapezoid or anything like that. And we want to know what is angle DAB plus angle BCD. So without any other information, can we figure out what the sum of these two angles has to be? And I know somebody said there's a theorem, and you can get the answer from the theorem. But I'd like to know, just using what we know about inscribed angles, can we, basically I'm asking you to prove the theorem. Is there a way that we can just compute what the sum of these two angles has to be using these circle theorems that we've learned?
So,
Yeah, Princeton?
yes.
Yep. Yep.
So, a quadrilateral that have been inscribed in a circle,
Yep.
they give you the 360 degree. So, measure angle A and C.
Yep.
The sum of A should be equal to 180 degree.
I mean, you need to say a little more than that, right? Because I mean, I can draw you if I could draw you a quadrilateral that's not inscribed in a circle. Let me draw you this one, where this here is maybe 30 degrees, this is 150 degrees, this is 30 degrees, and this is 150 degrees, right? And so let's say this is A, B, C, D. Well, in this case, if I look at angle A plus angle C, it's only 60 degrees, even though the entire thing is 360 degrees. Just because I add the two opposite angles in general doesn't mean that it has to add up to a full 180. In this case, these two angles add up to 60, and these two angles add up to 180, right? So now, of course, if you look at this diamond, what you see is that it can't be inscribed in a circle, okay? So there's something we have to use somehow that this quadrilateral is inscribed in a circle. That's what's going to help us add these two angles. Okay, so this I'm gonna kind of X out. This is not our situation, right? Because this can't be inscribed in a circle. Um, but it's not good enough to just say here's a quadrilateral. The sum of the two opposite angles is half the total sum. We have to use the circle somehow. So let's think about this angle A. Based on what we know for this circle theorems, this angle A is angle, DAB. What about the circle is equal to this angle? What can we use? What can we use? Is there an arc that we can say that the angle DAB is related to some arc in the circle? Well, what kind of angle is DAB in this circle? What kind of angle is it? I'm going to go erase this. So I have little space. So what kind of angle is DAB? We have a name for this kind of angle, right? Angle of DAB is what is it?
Is
Yeah,
it
no, Chris?
triangle?
Yeah, it's an inscribed angle, right? Right, it's an inscribed angle. Great. So what does that mean its measure is? So angle DAB is equal to, well, it's an inscribed angle, right? So it should be half the measure of the arc, right? Half of arc BD. And I'm going to be a little bit more careful here because, I mean, BD is really two different arcs. There's this arc and there's this arc. We want to say it's the opposite arc. It's this arc. So I'm going to call it arc BCD instead of arc BD. So DAB is equal to 1/2 the measure of arc BCD. Okay, right? This is the inscribed angle theorem. Okay, right? Because it's an inscribed angle, so the measure of the angle is half the measure of the arc. Great. Okay, now what about the other way? BCD. So this is the other angle that we need. So, oops, didn't mean to do that. Sorry. So also, angle BCD is, well, it's also an inscribed angle, right? This is also an inscribed angle, angle BCD. So what can we say about its measure? So angle BCD is equal to what from the inscribed angle theorem? What does the measure have to be equal to? It's in terms of some arc of this circle.
Yeah, let me try that.
Yep. Prince? Yeah.
Yeah, angle BCD is equal to half
hmm
arc, yeah, arc BC plus arc CD.
No, we got to be careful, right? Because BCD is an inscribed angle. So it doesn't need this averaging that you have when it's formed by two chords. When you have an inscribed angle, it's half of a certain arc. So it's the half
Okay.
of which arc? It's not going to be BC plus BD. It's the arc on the other side, right? So this angle here, BCD, right? It's half of this arc in the circle, right? So we could call it
Okay.
BA plus AD if we want, or I'll just call it BAD. Okay, so that's equal 1/2 the measure of arc BAD.
Okay.
Okay, that's what I'm going to call that. So this is good, right? Because we want to know what is the sum of these angles. Well, one of them is half of arc BCD. The other one is half of arc BAD, right? Because they're both inscribed angles. So let's see what happens when we add them together. So we get that angle DAB plus angle BCD. This is equal to 1/2 measure of arc BCD plus 1/2 measure of arc BAD. Right? I'm just adding the two equations together. Well, I can factor out the 1/2, right? So that's 1/2 measure of arc BCD plus measure of arc BAD. And now let's go look at this circle. What is, if I take arc BCD plus arc BAD, what is that giving me? I take one of these BD arcs plus the other BD arc.
Yeah,
What am I
they
covering
are
when I add
complete
them all up?
circle which is equal to 360 degrees.
360, right? Because it's covering the whole circle, right? BCD gives you this part of the circle, and BAD gives you the rest of the circle, right? So when you add them together, you get the entire circle, right? So this is equal to the whole circle. So it's 1/2 times 360 degrees, and that's equal to 180 degrees. Okay, so this is why the theorem works about quadrilaterals inscribed in circles. Okay, it doesn't work for any quadrilateral. You have to use these inscribed angles, right? That's what makes it work. So because these two opposite things are both inscribed angles in the same circle, you can show that they're half their respective arcs, and the arcs add up to 180, the arcs add up to 360 degrees. And that means that the angles will add up to 180 degrees. And if I just have some quadrilateral that doesn't go in a circle, and there's plenty of quadrilaterals that don't go in a circle, then you can't use this. And you get that the angles, the opposite angles, do not add up to 180 necessarily. Just like in the example that I drew. You can certainly draw quadrilaterals where the opposite angles don't add up to 180 degrees. Okay? All right, so that's why this works. So you just have to notice that both of these are inscribed angles, use the inscribed angle theorem, and then add. So it is a few things that you have to notice. All right, any questions on this example?
Yeah, yes, sir.
Yes, Prince?
Yes, so can this work with, because we're talking about quadrilateral, can it work with square?
Well, square is just a kind of quadrilateral, so yeah, that's sure. But a square, you already know that the opposite angles add to 180 degrees because they're all 90 degrees, right? But what this does tell you, so in fact, this is an if and only if, which I haven't proven to you. So in fact, if you have a quadrilateral whose opposite angles add to 180 degrees, then you can inscribe it in a circle. So I didn't prove that. We only proved the other direction. Remember, a statement is not equal to its converse. So here we're proving if you can inscribe it in a circle, then the opposite angles add to 180 degrees. Now, what's also true, but that we have not proven, is if the opposite angles add to 180 degrees, then you can inscribe it in a circle. So if we accept that as true for now, it is true, even though we didn't prove it, then what that says is that a square can be inscribed in a circle. Because if you look at a square, the opposite angles add up to 180 degrees. And that means you can always inscribe a square into a circle. Same thing with a rectangle, right? Rectangle, every angle is 90 degrees. So the opposite angles add to 180 degrees. And that means every rectangle can be inscribed in a circle. But there are plenty of other quadrilaterals where that's not true.
Hmm.
Okay.
So,
this is,
some are maybe the cat.
yeah. So let's say this actually right here. So I mean, this is exactly the consequence. We see if a quadrilateral can be inscribed in a circle, its opposite angles must add up to 180 degrees. So again, if I just draw some random quadrilateral like this, something like this, where I don't know, this is maybe 100 degrees, this is 90 degrees, this is 40 degrees, and this is 130 degrees. So these are all in degrees. Then this following quadrilateral here cannot be inscribed in a circle because the opposite angles don't add up to 180 degrees, right? So that doesn't work, right?
Okay, thank you so much.
And so I should say here's another fact, but that we didn't prove and we're not going to prove. So didn't prove is that if the opposite angles of a quadrilateral add up to 180 degrees, then the quadrilateral can be inscribed in a circle. Okay. And what we're really seeing is that we can think of this in terms of logic, right? We did logic before. So this, if a quadrilateral can be inscribed in a circle, we can call that statement P, and then the opposite angles add up to 180 degrees. We could call that statement Q. Then, in fact, we proved that P implies Q. But in fact, it's also true, although not automatic, also true that Q implies P. So what we actually get is that Q if and P if and only if Q, because the implication is true in both directions. Okay, so this statement right here is Q implies P. This statement is Q implies P. Okay. All right, any questions?
It's okay, there. We can go
Okay,
ahead.
great. Okay. Oh, Victor, can I please explain that again? Right. We have two statements. We have P, which is the statement a quadrilateral can be inscribed in a circle. And Q is the statement the opposite angles of the quadrilateral add up to 180 degrees. So what we just proved is that if P, then Q. So if the quadrilateral can be inscribed in a circle, then the opposite angles must add up to 180 degrees. This is what we proved, P then Q. But in fact, the other direction is also true. If the opposite angles of a quadrilateral add up to 180 degrees, then the quadrilateral can be inscribed in a circle. That's Q then P. That's Q implies P, or if Q then P. So it turns out that's also true, but I'm not going to prove it. Okay, so in fact, we have that a quadrilateral can be inscribed in a circle if and only if the opposite angles add up to 180 degrees. Okay, let's move on. Yeah, so I wanted to do one more angle result. So suppose two secant, there's one more kind of angle result that we can do. So I'm going to draw a circle here, and I'm going to draw a point outside the circle, A, and I'm going to draw two secant lines to the circle like this. So if this is B and this is C, and then over here I'm going to draw this secant line, this is D and this is E, then what the theorem says is that the angle A, so angle A is equal to half the difference between the measure of arc CE and arc BD. So measure of arc CE minus measure of arc BD. Okay. So this is
Yeah, yes,
this
sir.
is another angle result here. Yeah, question?
Yeah, Prince. Do we have any proof to show that show the difference, the arc of B and D to CE to become subtraction or use a minus sign between? Do you have any
Yeah, we're going to
proof?
prove this. Yeah, I'm just stating a result. We're going to give a justification. So the result is when you take this arc and subtract this arc and then cut that in half, that gives you the measure of the angle. So if this C to E were like, I don't know, 60 degrees, and this was 20 degrees, then you'd have 60 minus 20 is 40, and cut that in half is 20. That would tell you that this angle is 20 degrees. Okay, so if this were like an example, I'll just say, I can just do like a quick example, right? So if measure of arc CE is equal to 60 degrees and measure of arc BD is equal to 20 degrees, then angle A is equal to 1/2 60 degrees minus 20 degrees, or in other words, 20 degrees. So that would be an angle. That would be an example. Okay, but I'm going to justify this. So, but before I justify it, are there any questions on what the result is saying?
Where on a suit?
Good, good. Okay. So, all right. So why is this true? What's a justification? I'm going to draw the picture again, although I'm going to draw it a little bit smaller so that we have enough room to do the proof. So here's A. Do here. I'm going to just draw the same picture again. So this is B, this is C, this is D. Sorry. This is D, and this is E. Okay. So what line can we draw? So the way all of these things get proven, if you remember back to last week, is the way you want to prove basically anything in geometry that's a little bit hard, is that you want to just draw a line. You want to draw a line, and if you draw the right line, then basically everything is going to work out fine. So usually the kind of line you want to draw is going to be a line that connects 2 points in that connects 2 points that are already marked. So you actually have a few choices. You can basically draw any line you want, and it's going to help you prove it. But just for an example, let's see what happens if I draw line BE. I'm going to draw line BE, right? And remember, this is angle A. This is what we want to find out. Okay, so let's say I draw line BE. Okay, well, what do I have? Well, now this A is in a triangle, right? And so if I can figure out the other two angles of the triangle, then I win, right? So let's so the idea is calculate other two angles in triangle ABE. Yeah, this is going to be the idea. I want to calculate the other two angles in this triangle ABE. Well, angle E is not so bad, right? So, well, the first thing is if I want to do, well, what is angle BEA? Well, angle BEA is the same thing as angle BED, right? And it's the same angle, right? BEA, D is just a point along the line. So it doesn't change the angle whether I call it D or A. And well, this thing here is an inscribed angle, which means that its measure is arc BD, or sorry, 1/2 arc BD. Right, so this is 1/2 measure of arc BD, and that's because it's an inscribed angle. Right? Right, angle BEA, same thing as angle BED. That's an inscribed angle in the circle, so it's 1/2 arc BD. Is that okay? That clear? Okay, So what about the other angle? Well, if we want arc angle ABE, that's going to be the other angle in the triangle. Well, this is not quite so clear what to do because this angle doesn't immediately fall into any of our theorems. But what I can say is that look at this angle. If I look at angle BCE, these two angles together make up a straight line. So they have to add up to 180 degrees. And what that means is that angle ABE is going to be 180 degrees minus angle CBE. This is because the two angles add up to 180. The two angles add to 180 degrees, right? So one of them is 180 degrees minus the other one, right? Angle ABE is 180 degrees minus angle CBE. And now look at this angle CBE. What kind of angle is it? Again, it's an inscribed angle, just like all of these other ones. This is an inscribed angle, and that means its measure is 1/2 the measure of the arc. So this is equal to 180 degrees minus 1/2 the measure of the arc CE. Okay. Okay, so we're in a triangle. One of the angles is 1/2 measure of arc BD. The other angle is 180 degrees minus 1/2 of the measure of the arc CE. So now we can say since angle A plus angle BEA plus angle ABE equals 180 degrees because it's a triangle. This is a triangle. Now we just substitute, right? Angle A plus 1/2 measure of arc BD, right? This is angle BEA plus 180 degrees minus 1/2 measure of arc CE, because this is angle ABE, equals 180 degrees. And now this algebra is very easy to solve. The 180 degrees cancels with the 180 degrees. And when you move this to the other side, you end up just getting that angle A is equal to, well, we need to add measure of arc CE and subtract measure of arc BD. So it's 1/2 measure of arc CE minus 1/2 measure of arc BD, which is exactly the theorem. This is what we want to prove. Okay. So we draw a special line to make this triangle. And when we draw the special line to make this triangle, we now, well, if I want to figure out this angle, I figure out the other two angles. And once in a triangle, once I know two angles, I know the third angle. So I figure out this angle, it's an inscribed angle. I figure out this angle, it's not quite an inscribed angle, but it's 180 minus an inscribed angle. And so then once I have both of those expressions, then I can write it all up in an algebraic equation and solve it for angle A. Okay, so this shows me that angle A is half of the big arc minus half of the smaller arc, which is exactly what the theorem says. So in this way, we see that drawing this extra line BE actually gives us enough information to calculate angle A. Okay. Questions? Okay. Okay. So it turns out, I don't want to spend too much time on it. It turns out that we can prove the same result by drawing a different line. I'm not going to go through this proof, but I'm going to maybe leave it as an exercise. So I'm going to draw the same diagram here. Same diagram here. So this is A, B, C, D, E. And now instead of drawing the line BE, I'm going to draw the line CE. Okay? And so the hint to this other proof, we say hint, calculate angle CEA in terms of uh, arc CD, and then calculate angle ACE in terms of arc BE. Then use this to get an expression for angle A in terms of arc BD and arc CE. Okay, so this is a kind of sketch of a proof. I'll leave this as a hint for how to try to do the same result by drawing a different line. Okay, so this would give you a second proof of the same result. In the end, if you follow this through, you're going to get the same thing, that angle A is equal to 1/2 arc CE minus arc BD. But it's just going to be a slightly different way of getting there from drawing a different line. But if you notice, the theme is the same, right? The theme is you have some angle. How do you calculate it? Usually it's good to draw a line that completes a triangle. If you can draw a line that completes a triangle, that's going to help you figure these things out, because you can then use that the angles of a triangle add up to 180 degrees. Okay. Okay. So I'll leave that as an exercise. Okay, you can spend some time. We have 2 weeks actually until the next class, so you can spend some time thinking about it. Okay. All right, great. Okay, so final results. Ratios of chord lengths. This is going to be the last circle theorem. So suppose we have chords A, B, and C, D that intersect in a circle at a point E. No, I want a circle. Sorry. There we are. So I'm going to take here, I'm going to have a chord A, B, and I'm going to have a chord C, D. C and D. Okay? And the E is the point where they intersect. I'll label that E. So it turns out that when you have chords intersecting each other, that if you look at one chord and you look at the two segments that it's divided into, if you multiply these together, AE times AB, that's the same thing as CE times ED. So if you multiply the two parts of the segments here, that's equal to the product of the two parts of the segments here. So in the following diagram, let me just draw the diagram again. So if we have, that's not a circle. Let's try. Okay, so if we have a circle here, and I'm just going to draw a similar diagram. So this is A, this is B, this is C, and this is D. So let's say that this is 4 here, and this is 4, and this is 8. Well, then I can figure out the length of the other side. The other side needs to be 2, right? Because we need that 4 times 4 is equal to 8 times 2. Okay. So if you're given 3 of these line segments, you can compute the length of the fourth one. That length is going to be 2. Hey, this is sometimes this is called the power of a point theorem. Not really sure why it's called that. But if you want a name, this is a name for it. Power of a point theorem. Okay. So this is what the theorem says. If you have two chords that intersect each other, then the product of the two parts of one of the chords is equal to the product of the two parts of the other chord. Okay. Any questions about what this is saying? Let me put this 2 in red. I'm just going to write this in red. Okay, no questions? Okay. Okay. So let's justify this again. So the justification for this is we're going to use similar triangles to prove this result. So I just want to go back and just remind you about similar triangles. So we have that two triangles are similar if the angles of one triangle are equal to the angles of the other triangle. So I'm going to draw two triangles like this. That's one triangle. And then I'm going to draw another one, which kind of looks like the same triangle, but smaller, right? And so if this is A, B, oh wait, sorry, let me call these sides A, B, and C, and here I'm going to call these sides A, B, and C. Then when you have similar triangles, so one of the things that we know is there's a common ratio of the sides. So little a over big A is equal to little b over big B, which is equal to little c over big C. Try to make this C bigger so it's clear that it's big C. And I'll make this C smaller to make clear that it is small c. Okay. Okay. So this is similar triangles. And, one of the most important concepts in geometry. Okay, so these triangles are the same shape, they have the same angles, but they're not congruent because they don't have the same side lengths. But what they do have is this common ratio. If you take the ratio between a side of one triangle and the corresponding side of the other triangle, that ratio is the same no matter which side you choose. So that's the same as taking B over B, which is the same as taking C over C, or vice versa. Okay, so this is similar triangles. So what are we going to have here? So let me draw the same diagram that we have with the circle. So we're going to have our circle. We're going to have AB like this, B, and then we're going to have CD, and then they're meeting at E. And the question is, how can we draw lines to make similar triangles? There's a couple of choices that we can do. But it turns out, let's draw this line CA. Nope, no. CA, if I draw a line CA, and let me also draw a line BD. Okay, so I'm going to draw a line CA and BD. So my claim here is that triangle ACE is similar to triangle BDE. Okay. So I claim that the angles in this triangle are the same as the angles in this triangle. Well, why is it true? Well, these two angles are the same because this is the famous vertical angles theorem. When you have angles that are formed by two intersecting lines, the angles on opposite sides are the same. So, well, we have to show three different angles are the same, right? So, well, angle AEC equals angle BED by vertical angles theorem. Okay, when we have two angles, this is AEC and this is BED, these angles are opposite each other. They've got to be equal by the vertical angles theorem. So now I want to claim that CAB is equal to EDB, or which is the same thing as CDB. So now my claim is angle CAE is equal to angle EDB. Because why? Well, angle CAE is this angle. It's an inscribed angle cutting out arc BC. What about angle EDB, which is the same as angle CDB? This is also an inscribed angle, and it also cuts out the same arc BC. So we have two different inscribed angles here that both have the same arc. And if you've got two different inscribed angles with the same arc, then they're going to be the same angle because they're both equal to 1/2 the measure of the arc. Because, well, angle CAE equals, so let me write this down, it's the same as CAB, and angle EDB equals angle CDB, and both are inscribed angles with arc BC. Right, so both this angle and this angle are inscribed angles, and they both have the same arc that they cut out. Right, and so if I've got two inscribed angles that cut out the same arc, that means they've got to be the same angle. So they have the same
So
measure. Yes, Abraham.
Robert,
Abraham.
that is ABD is the same as ACD, right?
Yes, correct. So you could do that also for these angles. So that also gives you that this angle equals this angle. Right? ABD is the same thing as ACD for the same reason. So that's what's going to give you the third set of angles. Right? So both are inscribed angles with arc BC. So let me just say, so same measure, um, same measure. And then, right, so as Abraham said, we get the same thing. ACD is the same as ABD because they're both inscribed angles for arc AD. So those have the same measure too. So I'll add an extra page just to write this. So 3 angle, just need to remember, what is it? ACD equals angle ABD. ABD for the same reason with arc AD. So both are 1/2 times the measure of arc AD. Okay, so both of these angles here, CAB and CDB, are 1/2 the measure of arc BC, and then these ones here, ACD and ABD, are 1/2 the measure of arc AD. So we've shown that all three angles are equal. Maybe I'll just add this here, right? So I'll say, since all three angles of triangle ACE, what was it? ACE and BDE of triangle ACE equal the angles of BDE, the triangles are similar. Okay, we showed that all of the angles of one triangle are equal to angles of the other triangle. That means that they've got to be similar. Okay. All right, question. So we still haven't proven this. Eventually, we want to prove this statement about these ratios, or the statement about these products. But for now, I'm doing as a preliminary step, I'm saying first I'm going to draw these lines and show that these two triangles are similar. Once we get that these two triangles are similar, then we'll be able to prove this statement. But before we go on to that, any questions about why these two triangles are similar? Give me 1 second. I just have to move to a different room. And I got down about 120, 125. Okay. Can I eat the rest of it? Okay. There's a what? Oh, that. Okay, yeah, just leave that. Okay. Okay, good. All right, so if this is fine, let's say, okay, so these two triangles are similar. So what do we do now? So I need an extra page. So I'm going to draw the picture one more time. So I'm going to draw this circle again. Here's AB. Here's CD. I've drawn, let me do this in red again. Drawn this line, and I've drawn this line. Drawn this line, and I've drawn this line. And so we've shown that triangle, we call this E, triangle ACE is similar to triangle BD. So what does that tell us? Well, we have to know what are the corresponding sides. So this says, well, the corresponding sides are the ones that are opposite the same angles. So this angle E over here is equal to this angle E. So this tells us that AC over BD, so line AC over line BD, is equal to, well, now we know that this angle equals this angle, so we look at the opposite side. So that's CE is the opposite side here, and EB is the opposite side here. So that says that's equal to CE over EB. And that's also, if we look at this side, so we have, this is the side opposite this angle, so DE versus the side opposite this angle, which is AE. So this is going to be equal to AE over DE. In particular, what is it that we wanted to prove? We want to show that AE times EB equals CE times ED. So AE times EB equals CE times EB. That's exactly these two things over here and these two things over here, right? So by cross multiplying, we get that AE times EB is equal to CE times ED. I called it DE, ED, it's the same thing. Okay, so this gives you the final proof. Okay. Okay, so it's a bit of a complex proof, but it's a very easy result to remember, right? Because the result is just, this times this equals this times this. It's a very easy result to remember, but there's a lot underlying it, right? I mean, you've got to draw lines to make similar triangles. You've got to remember what similar triangles are. You've got to draw lines to make the similar triangles. You've got to prove that the triangles are similar, which uses these inscribed angle theorems. And then you've got to get the correct ratios of the sides in order to be able to get the final product that you want. So I would say this is a good test proof for circle theorems. If you can really understand why this proof works, then you have a very, very good understanding of circle theorems. Okay, so somehow if you study this, then you have a great full understanding of everything. Okay, so I think this is a nice last circle theorem to do. So any questions about this? It's a bit of a more complicated proof. Okay, so let's summarize. I think we're done. We're done with circle theorems. So let's summarize. So there's a theorem to measure the angle formed by basically any combination of two lines that you can think of in a circle. We've seen lines that meet at the center, lines that meet on the circle, a chord with a tangent, two chords, two secant lines that meet at a point outside the circle. Basically, any way that you can intersect two lines in a circle and form an angle, there's some theorem that tells you what the angle is, and it's in terms of arc measures. And most of these theorems, if you need to prove them, they can be proven by drawing a well-chosen line. Okay? Another ingredient that shows up repeatedly in these proofs is that two inscribed angles that intercept the same arc have the same measure. So this we used over here, right? We had an inscribed angle here and an inscribed angle here, and since they intercept the same arc, that means they have the same measure. And if you want to see a full catalog of the results, um, then you can find all of these in chapters 9 and 10 of the Art of Problem Solving, Volume 1. Okay, so of this book that I sent out. Okay. So all of these are things that you can find there. Okay, so this is the summary of circle theorems. Okay, so we did a lot of them, but they're kind of similar in the sense that, you're always comparing angles to arcs, and once you have inscribed angles, then you basically get everything else from just drawing the correct angle lines and using inscribed angles. Everything comes down to inscribed angles. And the inscribed angles proof is a little hard. So if you just want to accept that one, then you're in good shape. Okay, so we're going to leave circle theorems at this point. For the last 20 minutes, we're going to talk a little bit about differentiation and integration. So before we move on to that last 20 minutes, does anybody want to say anything further about circle theorems? Okay, great. Okay, so let's move on then. Okay, where are we? Okay, so let's move on. So we are gonna. So the next topic is this calculus topic, this differentiation and integration, which I want to just reprise what I mentioned at the very beginning of last year's workshop. So you may remember some of this, although it's been a long time. It's been a year and a half. So I want to spend a little bit of time brainstorming about what to do for this calculus workshop. But before that, I want to give the very basic ideas of differentiation and integration. So we did this already a year and a half ago, but I think it's worth reviewing. So the way I like to call these things, I like to call them the odometer problem and the speedometer problem. So if a car is driving in a straight line and we sit inside and watch the odometer, can we determine what speed the car is going at a given time? We're not watching the speedometer, right? If we watch the speedometer, we know what the speed of the car is. You just look at the speedometer and it tells you. But all that we're doing is watching the odometer. We're watching how many miles the car is driven, right? So if a car goes at constant speed, this is pretty easy, right? Because I'm going to draw a graph. This is two axes. One axis is time. The other axis is the odometer reading. And odometer reading, in other words, is just known as distance. And let's say I draw a line here that represents the reading. If we're going at a constant speed, then time is proportional to distance, or distance is proportional to time, right? And in this case, the speed is the slope of the line. Right? That's what speed is, right? You're going in a distance, you have a certain amount of distance that you travel divided by the amount of time. That quotient is the speed, right? This is just saying that speed equals distance divided by time. Okay. So this should be pretty straightforward. This is how we determine what speed the car is going at a given time. If the car is going at constant speed, I just see how much time it takes and how much distance I travel, and I can divide them, and that's going to give me the speed. Okay. Any questions on this? Okay. Pretty basic, right? No questions. Okay. Now, same question, but what if the car speeds up and slows down? So maybe the car is starting from a stop and then eventually, so I'm going to have my same axes. This is going to be time, and this is going to be the odometer reading. But let's say instead of what I had before, the car is going to start going very slowly and then it's going to accelerate. So maybe it looks something like this. Okay, maybe this is my reading. And let's say I want to know at some point over here, right, what is the speed here? Okay. So the odometer is telling you what is the speed here? And the idea is that a speed is a slope, right? We saw already when you're going at a constant speed, the speed is just the slope of the line. But when we go at a non-constant speed, what it turns out is that the speed is going to be the slope of the tangent line to the graph. Okay, so if I draw the tangent line here, so in this case, the speed is the slope of the tangent line to the graph. Okay, and in some sense, the point of differentiation is to be able to figure out this slope. So differentiation, the odometer problem is solved by differentiation. Differentiation is telling you how to figure out this slope. Okay, that's differentiation. Okay, because in general, if I just give you some function, without calculus, unless you use limits in calculus, with just kind of basic math, you can't really figure out the slope of a tangent line to some arbitrary function. Okay, you need calculus to be able to do that. For a straight line, it's easy. A straight line, constant speed, it's just distance over time. But here we have changing speed. You see that the further on we go, we're accelerating. This tangent line's getting steeper. We're starting with a horizontal tangent that basically means zero speed. And then as we move on, our speed is picking up, 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 up as we accelerate. Okay, so the speed at any given time, the instantaneous speed, is the slope of the tangent line to the graph. Okay, and this is the point of differentiation, is to be able to figure this out. Okay, so that's what I call the odometer problem. Figure out the speed from the odometer. Okay, and for today, I'm not going to say anything more than that. I'm just setting the stage. Okay, so we have a different problem, which I call the speedometer problem. So suppose a car is driving in a straight line and we sit inside and watch the speedometer. Can we determine how far the car has gone? And again, if the car goes at constant speed, this is easy. So now what I'm going to have is we're watching the speedometer. So I again have time on my horizontal axis, but this is going to be speed. My vertical axis is going to be speed because I'm watching the speedometer. That's my function. I'm looking at the speedometer, so it tells me my speed. And if we go at a constant speed, whatever this is, let's say for a certain amount of time, if I go at a constant speed, up until time, t over here, then this area over here is the distance. Right? So if I go at a constant speed, this is easy because distance equals speed times time. right? So the distance that I travel is equal to my speed times my time. And if my speed is constant, I just look at the speedometer and it says I'm going 30 miles an hour, and I sit there for an hour. That means I've gone 30 miles, right? I multiply the speed times the time. Okay. And this is geometrically, this is represented by this rectangle. Okay. So the speed is distance times time here when I go to constant speed. Okay, so you can see it on the graph. So now, same question, what happens if I slow down and speed up? So what happens if the car speeds up and slows down? Let me draw the same axes. So I have time down here on the bottom, and I have speed on this axis. Let's draw my same kind of curve. Let's say I'm going, oh no, wait, no, never mind. Let's say that I start off at a speed, and then I slow down for a little bit, and then I speed up, and then I average out over here to a constant speed. Wait, no, that's not what I want to do. Sorry, speed, I slow down, and then I speed up. Okay? So it turns out that the distance that I travel, in this case, it's just the same as on the previous thing. Here, the distance was the area under the speed graph. That was this distance, right? Because that gave me a product. Now, if my speed goes up and then goes down, the total distance is still going to be the area under the graph. Okay, the faster I'm going, the more distance I travel, and then when I get slower, it's getting me less distance. But the distance that I have here, up until some time t, the distance is still the area under the graph. Yes, this distance is the area under the graph. And integration is about how do we figure out the area under the graph. Okay, that's what integration is about. How do we figure out the area under the graph? Okay, so we have these two kind of geometric problems. One is, how do we figure out the slope of a tangent line to a curve? And the other problem is, how do we figure out the area under a line that might be curved, right? These are not regular geometric figures. And the way you solve the first problem is called differentiation. The way you solve the second problem is called integration. And they both have these interpretations based on a very kind of natural problem involving traveling, right? If you see the odometer, can you figure out your speed? That's the tangent line problem. Or if you see the speedometer, can you figure out your distance? That's the integration problem. So already you can see, maybe you remember the fundamental theorem of calculus, which basically says that differentiation and integration are reverse processes for each other. This is, at a very high level, this is why that's true. Because differentiation goes from the odometer to the speedometer, and integration goes from the speedometer to the odometer. That's why these things are inverse processes. Of course, that's not a proof, but it maybe gives you a little bit of intuition for what's going on. Okay, so for the last 5 minutes, I want to just brainstorm a little bit of workshop. Right, the area under the graph represents the total distance traveled. Yes, maybe I should say that specifically. So this area represents the total distance traveled. Okay. So differentiation integration, brainstorming a workshop. So this was the topic that most people wanted. So the key thing is we will only have 2 sessions for this workshop. So 2 sessions, these are going to be on March 26th and then April 16th. There's going to be a little bit of time off in between. Oh, sorry, not April. Yeah, April 16th. Yes. So these are going to be our only 2 sessions for differentiation integration. And so, of course, there's a lot of differentiation and integration that we can do. We did an entire year of this last year. For those who were in the workshop last year, we did an entire year of calculus. So if our focus is not just learning everything about differentiation and integration, but learning and preparing to lead a workshop that's specifically for high school teachers. So, what is the parts of differentiation and integration that we need as part of the high school curriculum, not as part of the university curriculum? For that, then maybe we can focus those 2 sessions on that and it won't be as ridiculous, right? We'll have enough time to hit the main points that we need for a differentiation and integration workshop that focuses on the high school level. So, what I want to ask you now, and you can answer vocally or by typing into the chat, or you can answer later by sending a WhatsApp message, is what are the absolute highlights that you have to do in order to cover the high school version of this because this is in the high school curriculum. So, what is necessary for students or for high school teachers to know on differentiation and integration in order to be able to teach the high school level of these topics? So, does anybody want to contribute something that absolutely has to be covered? So you can either contribute it now, or maybe later you can send a message to WhatsApp. I mean, so it may be that what we want to discuss is just spend a little bit more time on these pictures and why they work. But maybe that's not it. Maybe the students really need to know how to do some sort of calculus problems. And since I don't know the curriculum, I need to know like what are the kinds of calculus problems that a high school student might be asked to do, say on WAS or in, whatever other in a final exam or something like that.
Yes,
Yeah, Victor?
yes. Thank you for the presentation, and I appreciate. And exactly what you said for me, I would appreciate if I can send my comment later because, like exactly you said, we have to review the curriculum and see what are those things that are there, and also considering the what are those things that are involved. So based on that, we'll be able to make our contribution or our comments as to how the workshop is going to be like.
Okay, okay. That seems like a good idea. So let's say I request um, you to send me your ideas by March 19th. That's next week. Next week on Thursday. Uh, so I have time to plan the March 26th session. Okay, so this is for as many people as possible. If you can send me ideas by March 19th of how we should focus for two lectures on calculus, right? It's not all of calculus. We have to be very restrictive. So if you can send me those ideas within 1 week, then I'll have time to plan the session for the next week. Okay, so that's it. So reminder, there's no class next week. I'm going to be abroad. But then in 2 weeks, we'll continue our mini workshop on differentiation and integration. Okay, so thank you again, as always, for your attention. If you have not typed your name in yet, please do it because I'll stop the recording in a minute. All right, and everybody have a good couple of weeks, a good 2 weekends, and I'll speak to you soon. And I hope to hear some contributions from you over the next week. Okay, so I think everybody has typed their name in at this point. Great, so I'm going to stop the recording.